Okay, welcome to this lecture on diffusion. We're going to look at the atomic and sort of molecular scale models for how diffusion occurs through metals. We'll largely focus on our cubic packed systems for this. We'll touch on why this might be important for processing and what benefits we gain from deliberately diffusing one foreign material into another. And we'll look at how the rate of diffusion can be predicted based on some fundamental equations, and consider how diffusion may evolve based on structure and temperature. Okay. So what is diffusion? Diffusion is the mass transport by atomic motion. In earlier video, we considered the implications of increasing vacancy fraction in a metal as a function of temperature. And we were able to observe with an electron microscope movie that we saw islands at the surface growing in area. And the only way to explain this was that atoms were coming to that surface to contribute to that new area. And so involved in this process is the idea of both vacancies and thermal motion associated with atoms vibrating in that lattice of material. Okay, so some of the mechanisms there, we also see them, ideas there or models applied to gases and liquids. So we're going to, the fundamentals apply to random Brownian motion in those solids, in those physical states as well. And as mentioned in the solids, we rely more on here vacancies and interstitial sort of void spaces to help us translate matter through a lattice of a solid of one material. Okay, so with that idea, we can now consider some scenarios. For example, the formation of an alloy. This could be, say, copper and zinc, which you may know makes brass. So we could have copper on one side and zinc on the other. And so we start to consider the population of copper atoms as we transition across that interface, that boundary between the zinc and the copper. Okay, so this might represent the application of zinc onto copper, a plating of that zinc onto copper, and then later we may try to understand what happens to the zinc atoms. Does that interface stay as true as it was initially defined? Or do we observe an infusion of one metal into the other, as we would expect from understanding our Hume-Rothery rules and those being satisfied for substitutional solid solutions? So looking at the concentration profile, where we sort of have down here on the x-axis, essentially the distance in the material, x, and that distance has been chosen very carefully to be positioned right at that interface area. So if we're monitoring the concentration, let's say on this y-axis, for the concentration of copper, okay, concentrations usually use the square brackets. And, the opposite vertical here could be the concentration of, say, zinc, the gray. Initially, of course, we have mostly copper at 100% pure. And then, of course, it transitions very abruptly down to no copper, so zero concentration, as we transition across the X position here to the interface between the two. The zinc pattern, looking at the zinc concentration, is the opposite. No zinc in the pure copper, and once we reach that interface, now all of a sudden zinc builds up very quickly and we achieve 100% zinc. So here there is no alloy formation as of yet, and we have a simple pure interface between the two. Okay, now this scenario here has a lot of chemical potential, meaning we have a lot of order. We have an ordered interface, pure copper on one side, pure zinc on the other, and there's a driving force entropically to disorder that interface, provide more copper to the zinc area and more zinc to the copper area. And if that can outweigh some of the thermodynamic factors like activation energy and satisfy Hume-Rothery rules, we can drive atoms across the boundary. Okay, so this is what we mean when we say atoms tend to want to migrate from regions of high concentration to low concentration. So that is, after some time, perhaps not even with application of heat, we know that these concentration profiles will evolve into something more gradual, where deep in the copper we'll still have 100% copper there, but at some point we'll see that we've lost some copper atoms at the expense of having built up some zinc atoms in the material. And the sum of these, of course, adds to the total number of atoms present. And then eventually that copper kind of dies off to zero, where we have an area of pure zinc again, and we see that kind of building back up here. So diffusion basically is addressing how this interface has changed in this experiment, which forms a brass, as the copper and zinc in this example infuse into one another through a substitutional solid solution mechanism. Okay, so that was an obvious example where we asked two foreign materials to interface by and mix according to Hume-Rothery rules to predict that would occur. You might imagine, well, could copper atoms mix with themselves in the pure copper material? And of course they can. So there's a self-diffusion topic there. So in an elemental solid, its pure form, atoms can also migrate by similar mechanisms. So if you were able to atomically label certain atoms in copper, A, B, C, and D, what we would find is sometime later, these would be found in different locations due to self-diffusion. Okay, so again, here's a representation of that new location for all of those labeled atoms. Okay, so how does that happen? What are the mechanisms at play there? Well, atoms can't simply just magically appear and disappear at different atom locations, because those atom locations may be occupied. So we're going to see that in order to do this, we make use of vacancies to help us exchange atoms from one position to another. So an atom that is very close to a vacancy site has much more likelihood of occupying that vacancy and shifting that vacancy to a new spot. So a bit of a sort of switch there. And that would allow an exchange process. That is the exchange of an atom for a vacancy site. This is also the case for not only the pure metals, where the metals sort of diffuse within themselves, but this would also be the case when we have substitutional impurities like in the copper zinc. So of course, zinc can switch to that vacancy site and the copper can as well. Okay, so we find that vacancy diffusion, which helps mix two foreign materials at an interface as an example, the rate of the diffusion of one metal substitutionally into the solid solution, into the solid of the other, that rate depends on the number of vacancies and an activation energy for that exchange. Okay, so if we're going to shift one atom into a vacancy spot, it's going to take a bit of energy to break the bonding circumstance that exists on that atom and to position it in a new spot. So there's an activation energy there to help with that exchange. Okay, so we see here that the rate of substitutional diffusion across an interface depends on vacancy concentration, as you might imagine. The more vacancies we have, the more likely it is for atoms to make use of those vacancies to exchange positions, and how frequent they are jumping. So that has something to do with the activation energy. Okay, so those two are related. Okay, So this sort of animation here is showing those steps that we referred to earlier. We can see how both zinc and copper have had atoms switch positions by way of utilizing a nearby vacancy for the exchange. Okay, so that has allowed us to think about metals and the atoms in packed unit cells or packed lattices to occupy other spots by way of a vacancy. Well, as we've seen before, there are some interstitial sites in many metals, and we can locate smaller atoms in those interstitial sites. So here's an example. Say, for example, carbon could be located into a lattice of iron atoms, and the carbon is small enough to fit into the empty spots not occupied by BCC or FCC packing. Okay, so the interstitial spots here are available, and we can locate carbon in those spots. Okay. So what we know about interstitial diffusion is that the availability of vacancies is much higher, if you want. There are plenty of interstitial sites available, far outnumbering those that would be vacancies in the iron atom positions. So we would expect that if the concentration of vacancies helps with the rate of diffusion of an interstitial feature, like a carbon atom in iron, well, that carbon atom has lots of options for nearby interstitial vacancies. So that is, we expect the vacancy count of interstitial sites to be higher, and that's going to allow for the rate of this interstitial diffusion to be a lot higher. Okay, so why would all this be important? Well, as you might expect, if we can pack more atoms to a unit area or into a unit volume, we are densifying the material, and we will later see that this helps make additional bonding and makes for the propagation of stress through the material much more difficult, where we can no longer slip planes of atoms past other planes of atoms by way of having to break many bonds as we slip those planes of atoms past their neighbors. But if we have additional interstitial atoms that are present, there's even more atoms to break due to those interstitial atoms bonding to neighboring iron atoms, for example. So this is what's done to case harden iron to make steel. And so an example here would be, for example, a gear, which has to undergo a lot of mechanical load and shear as the teeth of that gear move past other cogs or gears and those teeth. And so the casing, the outer edges of that, if we could infuse carbon into that pure iron, that would case harden, provide a harder case around that outer material, and this would allow the material to sort of be more resilient in its service, in its ultimate application. Okay, so another example where this is done is transforming silicon to be more conductive. And so what is done is silicon, pure silicon, is actually a poor conductor. But if you can infuse the silicon lattice with neighbor atoms from the periodic table, which have more or less electrons than the silicon atom, per atom, of course, we can make use of those new and different types of atoms to enhance the conductivity. So this is what makes, in this case, with phosphorus having more electrons per atom than silicon as far as valence electrons, this is what makes an N-type semiconductor. If we can infuse phosphorus into the silicon or dope it with phosphorus. So the process might exist with that pure silicon lattice, rows of atoms in perfect kind of order of silicon. And then onto the surface, we might deposit a phosphorus containing molecule or directly deposit atoms of phosphorus right onto that surface. We've learned now that by waiting time or applying temperature or both, that we would expect diffusion across that interface for where the phosphorus meets that silicon, and there's a driving force to bring that phosphorus in to the silicon and allow mixing between the two. Okay, so after heating, in this case, to accelerate the process, providing energy to overcome activation energy for exchange, making use of vacancies, in this case of silicon, we can get phosphorus to infuse into that silicon and occupy some sites. And so what you're seeing here are electron microscope images where we can see the computer chip that relies on patterns of this N-type silicon, sort of the features here, might be a feature there. And below it, we can see elemental maps. So a technique called energy dispersive X-ray scattering can lead to pixels that are generated only from silicon atoms that may be present. So we can see here the white pixels indicate the area of pure silicon. And then the image below is the contrast complement. So it's the opposite shading, if you want. And now we see the white pixels are indicating the presence of aluminum. So in this case, aluminum has been infused by a diffusion process analogous to what we said here for phosphorus. And we can see that aluminum is present in the white pixel areas in the bottom image, indicating that diffusion